Okay, more electrical components and circuits. So we're going to talk about semiconductors. Semiconductors are primarily made from silicon or germanium. There's some high frequency types that are made out of gallium arsenide and some materials like that. But we won't be talking about those. Basically just silicon and germanium. Some of the first devices were made out of germanium, and we still use germanium for some of the small signal diodes. Mostly everything is silicon based. When you talk about silicon, it's a crystalline structure. And we talk about three types. We have what we call intrinsic silicon, which is pure silicon. And it has a very nice crystalline structure because it has four electrons in its outer shell, and they will combine with the other atoms and make what we call covalent bonds, and it makes a really nice crystal. People found out that if they introduce impurities into the silicon, they can make what we call P-type or N-type silicon, where the P-type will have a positive net charge instead of being neutral, and the N-type will have a negative charge instead of being neutral.
How do they know what's what? I mean, through trial and error, and they figured out what that made it positive and what negative?
We'll get to that in a minute.
All righty.
And when we talk about the P-type and N-type, there's going to be what we call an energy band gap between the valence and the conduction band, and I'll talk more about that. The thing to remember is if it's a silicon device, it has a band gap or threshold voltage of 0.7 volts. If it's germanium, it's 0.3 volts. Now these are approximations,
right?
Because you'll see on a graph, it's on what we call the knee. So that's approximately where the curve starts.
Curving, yeah.
Okay, so if we look at a silicon atom, you'll see that its outer shell has four what we call valence electrons. We call that the valence shell. And if you remember, there's an equal number of electrons and protons. So an atom is neutral as long as it hasn't lost or gained an electron. So if we look at the crystalline structure over here, you can see all these silicon atoms are all very happy, and they're sharing electrons in that outer shell, and it makes really nice, pretty white crystals. So if we take that and we, for instance, add boron, and we won't talk about how they do this, but they manage to get these impurities as they grow the crystal. You'll see that boron is an atom that only has 3 electrons in its valence shell. So when they're in that crystalline structure, you wind up with a hole because there's no 4th electron.
Right.
So since it's missing an electron, it has a net positive charge.
Mm-hmm.
Likewise, if we add phosphorus, and these are not the only two things that they use, but some of the most common. Phosphorus has 5 electrons in its outer shell. So when those are in the crystal, we wind up with an excess electron that can't bind with anybody.
Right.
So it's negative. So now I have a piece of silicon that has a positive charge and a piece of silicon that has a negative charge. If I put them together, it's going to become what we call a p-n junction. And that will make what we call a diode, which is the most basic semiconductor. So a diode has 2 electrodes, one attached to the P material, one attached to the N material, and we call the electrode attached to the P material the anode, and the one attached to the N material we call the cathode. On the actual devices, a lot of times the cathode end is marked with a stripe, a white or a black stripe, to indicate that's the cathode, because it kind of looks like a resistor with 2 wires coming out.
I got you.
And I have a picture, I think, on the next slide. When we forward bias that p-n junction or that diode, and we're applying a positive voltage on the anode with respect to the cathode, it will conduct current provided that that voltage is more than that threshold voltage we talked about, which would be 0.7 volts if it was silicon and 0.3 volts if it was germanium. So if we have less voltage than that, it won't conduct. If we reverse the voltage, it will not conduct up to a point. And we'll talk about that in a bit. But for most purposes, it only conducts in one direction when you have a high enough voltage to overcome that threshold voltage. We call that the forward voltage drop.
Okay.
This is just a diagram showing when we have N material and P material, at the junction, it kind of forms what we call a depletion layer, where positive ions are attracted to one end and negative ions or electrons to the other. And it's this depletion layer that we have to overcome. And you can see it's represented by effectively a little battery because it produces a voltage. So in order to conduct, we have to have a voltage higher than that. And that's that threshold voltage we talked about, the 0.7 or the 0.3. It just kind of shows what the voltage looks like across the junction. This is just another showing the way that the the positive ions move and the negative ions move. And in this case, it has a very small depletion layer. We'll talk about depletion layer a little more, I think, on transistors and some of the other types of diodes. The schematic symbol we use is this triangle with a bar. That vertical bar represents the cathode, or the stripe that we'll see on it. And the triangle is showing the way current would flow from positive to negative. Any questions on those?
I don't think so.
The important things are the anode and the cathode.
Mm-hmm.
Uh, just another example of this. The symbol that we use in conventional current flow is going positive to negative. If you look at this graph, okay, it's showing current versus voltage. So you can see the current is very low. There's some leakage current until we get up to what we call the knee. And that's where we see this 0.3 or 0.7 volts. And then it starts to conduct. And the slope of that line is going to be determined by its internal resistance. If it was a perfect inductor, this would be perfectly, would be infinite current. But because it's real, and I said inductor, diode, it's got some internal resistance. So that's why you see this as a sloped line. If we apply a reverse voltage, okay, it won't conduct. Again, you'll have a very small amount of leakage in the microamp range until we get to this point we call the Zener breakdown or avalanche region. And if you get a high enough reverse voltage, it will start to conduct. It turns out we use that to make Zener diodes. And we purposely use them in reverse, and they can manufacture them so that breakdown voltage is very precise. You can get a Zener diode that conducts at 9.2 volts if you want. And we use those as voltage reference sources a lot. But the typical diode is going to operate over here on the right-hand side. Here's a typical, this happens to be a germanium, ON4148. It's been around for decades and decades. You see the black stripe, which indicates the cathode end. In this one, it's in glass, and you can actually see the p-n junction here in the middle. And this is the symbol that we use, showing the anode and the cathode. So what electric component allows current to flow in only one direction?
Charlie.
What are the names for the electrodes in the diode?
Charlie.
How is the cathode lead of a semiconductor diode often marked on the package?
With the word cathode, with a stripe, B, bravo.
Bravo is good. Now you notice they said a semiconductor diode because we also have vacuum tube diodes. They were here before semiconductor diodes.
Yeah, like the old TV sets.
Yep.
Yeah, I remember my dad taking it apart. He had this big circular thing you'd plug in. It was like magnetic. It was super magnetic, and he'd do this around the
Degaussing coil.
What was it called?
Because sometimes you get a magnetic field on the cathode ray tube, and you'd use that to get rid of it. Otherwise, it would mess up if it was a color tube, especially, it would mess up the picture. And later ones, they had that built in. It would automatically do that every time you turned it on. Which is true about forward voltage drop in a diode? It's kind of a tricky one, but just read the answers.
Well, it's either Alpha or Bravo, I think. I say
Which
Alpha.
one do you want to go with?
I'll go with Alpha. 50-50.
Very good.
Ah,
It's 0.3 in germanium and 0.7 in silicon.
he's right there in front of me.
And it's also different numbers in other materials. And we'll talk about those here in a bit for light emitting diodes aren't germanium or silicon. And we'll talk about them right now.
There we go. Flashlights.
Well, yeah. And indicator lights,
Mm-hmm.
they come in all kinds of colors now.
Yeah.
And they use different material to produce the different colors. And each of those materials has a different forward voltage. So instead of it being 0.3 or 0.7, it might be 2.5 or 3.5. Gotcha. They're all different voltages, but they're still diodes, and they have to be forward biased to emit visible light. And that's why they're in these kind of clear packages. In the ones shown here, the plastic that they're in is colored to affect the color of the light, but in some cases, it sort of enhances it. The color of the light is in the basic diode being emitted also.
Gotcha.
We use them as indicators for something being on or off, like maybe a red light if it's an error type indicator.
Right.
They're used as digital readouts. If you've seen a lot of the old 7-segment displays where they have these little diodes embedded to make a number or letter.
Oh yeah. Mm-hmm.
They work pretty much the same way, but because it's different material, they have a different band gap. And this chart over here is showing it's again current versus voltage, and you can see where all these different colors behave differently as far as the amount of voltage it takes and what color light they're going to produce. These don't have a stripe because they don't have two wires coming out. And what we do is cut when they make them, one of the leads is shorter than the other. That's the cathode. The longer lead is the anode. Also, you can't really tell here, but it has this little rim.
Mm-hmm. Yeah.
It'll have a flat spot on the cathode side.
Huh. Now you're gonna make me look at one.
So what causes a light emitting diode to emit light?
Alpha.
Good. Which of the following is commonly used as a visual indicator?
Alpha.
These are hard.
Yeah, the other ones I have no idea.
Okay, so now we know all about diodes. So we're going to talk about transistors. So some people discovered, there's actually some people working at Bell Labs, that if you take that p-n junction that we made for a diode and you add another piece of material and we make it a PNP junction, I can now control the amount of current through that device. Instead of it just passing current in one direction, I can now not only have it pass current in one direction, but I control how much current it passes. And I do that by using that middle piece of silicon. And we can have two types. we can have a PNP or we can have an NPN. And it's just whether it has two pieces of P-type material on the outside and N in the middle, or just the opposite. And they behave oppositely. So that's called a basic bipolar junction transistor. And it's a current controlled device. So applying current on what we'll call the base, which is the middle piece of material, will control the amount of current that goes from the collector to the emitter. So in this device, we'll have three terminals, three electrodes, and we call them the collector, the base, and the emitter. The emitter is like the cathode on your diode. The collector is like the anode on the diode, but we now have this thing in the middle we call a base, and that's what we use to control the amount of current through it. If we were to supply a negative current or a negative voltage to the base, it wouldn't conduct if it was a NPN. You just the opposite if it was a PNP. Later, actually, they had discovered a field effect transistor before the bipolar junction, but they didn't really know what it was. So it was only later that they actually really rediscovered it. And it will also control the current through it. But in this case, it's by applying a voltage, not a current. So we apply a voltage to the controlling terminal, which in this case we call a gate. And you'll see more of these, I think, on the next chart. So there's no current flow. It's using an electric field to control the amount of current that flows between what we call the source and drain, which are sort of equivalent to the collector and emitter. And again, you can have two types, N channel or P channel, depending on whether, it's two P's and one N or two N's and one P. So the main thing is on a bipolar junction, remember that the current input controls the current output. And we're, again, it's made up of the P-type material and the N-type material. Three electrodes for the bipolar are emitter, base, and collector. And we show them over here, and you see the three types of silicon. And this is what we call an NPN. So the collector would be equivalent to the anode. The emitter is equivalent to the cathode. And the B for the base is the controlling element. So if there's a voltage between the emitter and the base, it will cause current to flow, just like this was a diode. This is a PN junction. So if we apply more than the threshold voltage, if this was a silicon device, once we get above 0.7 volts, this will start to conduct from the base to the emitter. And that causes kind of an avalanche effect of current flowing from the collector to the emitter, which is much greater than the current that flows from the base to the emitter. And that's how we get amplification. So a small amount of current going from the base to emitter can control a large amount of current going from the collector to the emitter. And that's called voltage gain or power gain. Any questions on bipolars?
No, not really.
Okay. Here are the symbols we use, and I think this will show up in the next session where we talk about schematics. So this is the schematic diagram for an NPN bipolar transistor. And this is a PNP. You notice on the NPN,
the direction of the arrow.
You have this little arrow, and it's showing that this is the PN junction between the base and the emitter. It's basically this diode, and it conducts in this direction. So when you have current flowing here, it allows current to flow this way. Likewise, on the PNP, you have current flowing from the emitter to the base, and that causes current to flow from the emitter to the collector. So it behaves just the opposite. The NPNs, I think, are far more prevalent than the PNPs, but you find both types. But exam questions will ask about the collector, the base, and the emitter, and what the symbol is. This is a kind of a slice through what the silicon device would actually look like, where you have this base N material, some P material, which becomes your base, and some more N material, which becomes the emitter. So this junction along here is your diode, just like we had in a single diode. And current flowing that way causes current to flow this way. And we won't go into the physics of what's happening.
Good, because I'm like,
just believe me. And this is kind of showing more of what's happening. Again, we have that depletion zone just like we did in the diode. It extends a little bit farther because we have some extra material, and we won't go into that, but that has an effect on how the current flows through the transistor. It has a property we call transconductance, which you don't have to remember. It's kind of like how the conductance is controlled by the base signal. And you can see here, we're applying a very small AC signal on the base over here. And it's causing that alternating current to flow because this is biased positively on. Okay, it's above 0.7 volts. So we vary that input voltage. It's still enough to conduct. And the current through the collector to the emitter is going to be along this line. We call that the load line. And you can see that it's a much greater signal than what we put in. That's called amplification. We could also use this device as a switch, and we can provide a low enough voltage or current that it doesn't conduct or it's off, or we can apply a high enough one that it's way up here in what we call saturation, and it's conducting as much as it possibly can, so it's either on or off. Right. But we control whether it's on or off. So which of the following components can consist of 3 regions of semiconductor material?
Bravo.
What are the names of the electrodes of a bipolar junction transistor?
Bravo.
A field effect transistor, the input voltage controls the current instead of a current through the control element. It's got three regions, just like the bipolar. We call them the gate, the drain, and the source. In this case, the source, and by the time they did these, they learned that electrons flow opposite to conventional current. So they named the source equivalent to what would be the emitter or the cathode, because that's the source of the electrons. The drain would be equivalent to the anode or the collector on the other devices, and that's where the electrons come out. So they go in the source, they come out the drain. We control them with a voltage on the gate. And again, you can have a P-type channel or an N-type channel, and like the bipolar, they work opposite to one another. In one case, a positive voltage will cause current flow. In the other case, a negative voltage will cause current flow. They use a different symbol, and it's this bar. It kind of represents the channel that the electrons flow through. And the gate is just another element that's providing an electric field between the body of this device and the gate. And that electric field, the strength of that electric field is what's controlling the current flow. So we have an N channel, which is showing, in essence, a positive voltage going in, and a P channel, which is positive voltage coming out, or a negative on there. If we try to show the device, you can see that it has two P silicon elements with the N in the middle. And that is the gate in this case. And it's also the junction where current flows from conventional current would go drain to source, electrons would go source to drain. These are just kind of trying to show something about the electrical fields, but you can't see it very well. Here's another plot similar to what we did for the bipolar, and it's showing where we're using this device as a switch, or can use it as a switch. And down here, at this pinch-off voltage, it's not going to conduct. So the device is off. If we apply enough voltage on the gate to get it up to the saturation region, it's fully on or conducting. If we operate at gate voltages in the middle, okay, that will determine how much current flows. So we can also use this device not only as a switch, but as an amplifier. Except in this case, the output is proportional to the voltage on the gate, where in the bipolar, the output was proportional to the current going through the gate, of the base. This is just another cross-section. In this case, it's showing a metallic oxide field effect transistor, where instead of the junction, we actually have this plate that the gate, a metallic plate the gate is connected to, separated by an insulator, so it's almost like a capacitor, because we create an electric field in this region. And that's what's controlling the current that's flowing, the electrons going from drain to source, electrons going source to drain, or the conventional current going drain to source. So what does the abbreviation FET stand for?
Delta.
Very good. What type of transistor has a gate, drain, and source?
Bravo.
Bravo. Okay, so transistors, we can use them as switches, whether they're field effect or bipolar. They operate them in the saturation or cutoff regions. As amplifiers, they amplify the signal proportional to the current or the voltage, depending on whether it's a bipolar or a field effect device. And we call that amplification gain, which is the ratio of the output to the input. That's one of the things we talked about last week, where we measure it in decibels. So the gain in decibels would be, actually in this, the 10 is left out. It should be 10 times the log of the output over the input. So if the output was 10 times the input, it would have a gain of 10 decibels. If it was 100, then it would be 20 decibels. I'm sure you remember that from last week, right?
Mm-hmm. Not entirely. I remember a lot of the terminology, the formulas are still, I was trying to get them.
Well, that's about all you need.
Okay.
This is just another chart showing how we operate a bipolar transistor. And this load line is the load resistor or amount of load that's connected to the transistor. And the current across that, varying current across that load is where you see the varying output voltage. So which of these components can be used as an electronic switch?
Which of these can we do that? Charlie.
And now don't get that confused. A little later, where we're going to talk about an electric switch, which is a relay. This is an electronic switch. Because a relay is a mechanical device that's controlled electrically. So you don't want to confuse them.
Okay.
What is the term that describes a device's ability to amplify a signal?
Alpha, gain.
Which of the following can provide power gain?
Bravo.
Right. Transformers can provide voltage or current gain, but there's no power gain. Power going into a transformer is equal or less coming out.
Usually less. I'm just thinking the transformer outside my house that was going bad.
Yeah, well, they're doing voltage gain. Well, actually, voltage loss, because it's a step-down transformer. It's probably 16,000 volts, and it's dropping it down to 220.
Yep.
Reactors, I guess, if it's a nuclear reactor, can produce power. Resistors only consume power, so there's no power gain. Okay, so we learned diodes conduct current in one direction, with the exception of a Zener diode,
Right.
special purpose. You have to forward bias the diodes, either 0.3 volts for germanium or 0.7 for silicon. And these are approximations. Diodes have anodes and cathodes, and we mark the cathode with a stripe, unless it's an LED. And there we have a shorter lead for the cathode and a flat spot. LEDs only emit light when they're forward biased. Transistors have power gain, and they can be used as a switch or an amplifier. We can have bipolar transistors, which have base collector and emitter electrodes, and there's both NPN and PNP types. We can have field effect transistors, which have a gate, a drain, and a source. And again, they can be used as switches or amplifiers, and they have NPN and PNP versions.